Greetings, welcome to the 16th lesson in a series of lessons on basics of power systems engineering. This presentation is part 2 of a 3-part lesson that covers power in single-phase AC systems. In lesson 16, I used the circuits seen on this page to explain power in single-phase AC circuits. The load in this circuit is known as an inductive load because the imaginary part of the load impedance is a positive number, plus 8 in this case. To gain experience with another type of load known as capacitive load, I'll change the load impedance from 20 plus J8 to 20 minus J8 and calculate the powers. Here is a circuit with the capacitive load 20 minus J8. I'll find the current in the circuit first. Source voltage divided by the total impedance gives me the phasor for the current. Total impedance, of course, is the sum of the line impedance, which is 1 plus J2, and the load impedance, which is 20 minus J8. You see that sum in the denominator. Simplifying, I get 220 with 0 over 21 minus J6, and that comes to this complex value for the current phasor, and converting that into polar format gives me 10.07 amps with 15.95 degrees positive degree angle. The load voltage can be found by multiplying this current into the load impedance. So here we have the current that was just found that goes through this circuit, multiplied by the load impedance, which is 20 minus J8, to get the load voltage here, plus or minus. And load voltage comes to 217 volts with negative 5.856 degrees as its phase angle. Here are the load voltage and current for our later reference. We can find the source apparent power by multiplying the magnitude of the source voltage by the magnitude of the current. Here is the equation, S equals magnitude of V times magnitude of I. So the components are scalar, and the product also is a scalar real value that we obtain for S. Here's the apparent power of the source by multiplying the source voltage, 220, times the source current, again, just the magnitudes, and the product comes to 2,215 volt amperes or 2.215 kilovolt amperes. For the load apparent power, we'll do something similar. The magnitude of the voltage for the load, 217 times the current, it's the same current, and the answer comes to 2,185 volt amperes for the apparent power of the load. I would like to take a short detour at this point to introduce myself. My name is Fouad Albandi. I am a PE in electrical power engineering. This is the 16th lesson in a series of lessons on basics of electrical power engineering that I have published on the YouTube. You'll find my name and web address and email address on this page. I invite you to visit my website for comprehensive modules on power systems engineering topics. My website is at own-your-destiny.mylearnworlds.com. I will now continue the work with our example, finding complex powers of the different elements of this circuit. Complex power is found in one of 3 ways. It's found by multiplying voltage phasor by complex conjugate of the current phasor. That's one way, seen here. Or we can find it by multiplying square of the magnitude of the current times the impedance. So this is the current through the circuit, and we take its magnitude, square it, and multiply by, for example, by Z if we were to find the complex power of the load, or multiply it by this impedance, the line impedance, if we were interested in the power loss in the line, or the complex power of the line. Or by dividing the square of magnitude of the voltage over the complex conjugate of the impedance. So that's the third way of finding it. Again, V here is a scalar number. It's the magnitude of the voltage. So it would be 220 for the source. It would be 217 for the load. Divide by the conjugate of the impedance. Of course, we cannot use this method for the source because there is no impedance associated with the source. So the only way to find the complex power of the source is to use this top one. But for the other elements, we can use any one of these three methods or three formulas. For calculation of the load complex power, I'll choose the top one to use. Here it is, S equals V times I conjugate. The asterisk indicates conjugate. The voltage phasor for the load is this one, 217 with negative 5.856 degrees, multiplied by the current conjugate. So this is the current, and asterisk indicates that before multiplying, we need to find its conjugate. You find the conjugate of a phasor that's given in polar format by inverting the sign of its angle from positive to negative, or if it were negative, from negative to positive. So here the angle was plus 15.95. I changed it to negative 15.95. Everything else remains the same. Multiplying those two, S comes to 2185 with this degree angle. Complex power is best expressed in Cartesian or rectangular format and not in polar format, because in the rectangular format, the active and reactive power components of the complex power are directly visible. So I'm going to put this in Cartesian or rectangular format, which is seen here. 2029 minus J 811.7. The real part of the complex power gives the real power of the load, this number, and the imaginary part gives the reactive power of the load, this number here, with the negative sign. Writing it out explicitly as P plus JQ, we see that P equals 2029 watts and Q equals negative 811.7 vars. The positive sign of the active power in here indicates that the load is consuming 2029 watts of active power, and the negative sign of the reactive power, this one, means that the load is generating 811.7 vars of reactive power. Here they are for later use. I will now calculate the complex power loss in the line in this impedance 1 plus J2. Since we have the current through the impedance I and we have the impedance itself, I'm going to use the I squared Z form of calculation of complex power for this. And here it is, S equals I squared Z. Of course, Z here is this impedance, 1 plus J2. Substituting for the magnitudes of the current and the impedance, we'll have S equals 10.07 squared, and that's the magnitude of the current, squared times the complex impedance of the line, 1 plus J2. The answer comes to 101.4 plus J 202.8. It is seen that the real power loss in the line is 101.4 watts and the reactive power loss is 202.8. Because the line is seen as a load actually by the source, the positive quantities mean power that's absorbed by the line, which will then use the loss term, power loss in the line. But it's the same, has the same nature of power that's absorbed in a load. Here are the two quantities, real and reactive power, and I'll save those for later use over here. I'll now calculate the source complex power. As I said, for the source complex power, we can only use this formula. And we have the V and the I as two phasors, seen here and here. Substituting, we have 220 with 0 times 107 with 15.95, conjugated right here. So here's the conjugate of current, here is the voltage of the source. The product comes to 2130 minus J 608.8. Separating those, the real part, P equals 2130 watts and Q is negative 608.8 VARs. Since the active power of the source is positive, it means that the source is providing the amount of 2130 watts of power to the circuit, seen here. And on the other hand, since the reactive power of the source is negative, it means that the source is absorbing the amount of 608.8 VARs from the circuit. To review, positive power, if calculated for source, means source is providing that power. But if that positive power is calculated for load, it means that load is absorbing that power. On the other hand, negative power calculated for source means that source is absorbing that power, but a negative power calculated for load means that load is providing that power, such as the case is in this example. Inductive loads and lines consume reactive power, and capacitive loads, such as the load in this example, provide or deliver reactive power. Let's look at the balance of power in the circuit. Some of the real power absorbed by the load and by the line should equal the real power generated by the source, which means that adding these two powers, one for load and one for line, they should add up to this number, which is the power generated by the source. Here you see the math for that. The sum of these two equals 2130.4. 0.4 is just from rounding error, so they're identical. And similarly, the algebraic sum of the reactive load power and reactive line power should add up to source reactive power. So adding these two together, considering their signs, we should get this value here. And you see that in the last line here, negative 811.7 plus 202.8 comes to negative 608.9, which is identical to, almost identical to this. Difference is only 0.1 VAR. Another interpretation of this equation is that 202.8 VARs of the 811.7 VARs of power that was generated by the load has been lost in the line, and the rest, which is 608.9 VARs, is absorbed by the source. Let me put those values on the diagram here. So the source is generating 811.7 VARs, And out of that, the line is consuming 202.8 vars of that, and the remaining vars, which is the difference of these two, the difference between these two, is going to be absorbed by the source. So the difference, which is 608.9 or 608.8, goes into the source. The fact that capacitive loads generate reactive power and deliver it to the circuit is used in correcting low power factor of inductive loads by placing capacitors in parallel with them. I'll cover power factor correction in part 3 of the AC power series of lectures under lesson 17. We are now at the end of lesson 16. If you enjoy watching my channel, please click on the subscribe button and notification bell. If you're looking for a resource to review topics in preparation to take the PE exam in electrical power engineering, you may find the modules on my website to be useful for you. Thanks for watching this video, and I hope to see you soon in another one of my presentations.